And so this is SIG Scalability meeting, 9th December 2021. And today we have, I think, two topics that we want to discuss. I remember that the first one was added by Mike, but I'm not sure if Mike is here. So I guess
yeah, let's start with the second one, maybe.
Yeah.
You would that one, right? Oh yeah, so that's me. So I have a short presentation for you. Let me share my screen first. I cannot. Host disabled screen sharing. Can you do that something about it?
Honestly, I never done it, but probably yeah.
I can't remember how exactly you do that, but I think
I need to stop, and then I can make a host.
I think there's like I'm actually not logged in as an admin now, but I think you need to make Łukasz a co-host, which is like in the participants list you can do something.
Okay, I did it. So can you try now?
Okay. Trying. Oh yeah. Chrome. One second. I think I need to drop off and reconnect. Permission issue. Sorry for that. We'll be back in 1 second.
Okay. So actually, Wojtek, are you familiar with the sub-second precision of those watch events that Mike was mentioning?
I've seen a PR in a perf test repo, which was like mostly, which is basically for tracking like the requests from coming purely from cluster loader, not like all the events. So if this is about this, I'm somewhat familiar with that. But yeah, I like let's maybe go with
yeah.
All right, thanks. So can you see
yes.
a graph diagram? Okay.
Yeah.
Cool.
Yes.
All right. So like in general, I want to show you something I've been working on quite recently. I call it API streaming. And the first thing is this diagram. So it shows memory consumption of an API server during a test. And the test I did was as follows. So create a namespace, put 400 secrets in it, each secret containing 1 megabyte of data. So quite huge, quite heavy. And then start informers and measure memory consumption. And here's the metric I used for
Sorry,
memory
so
consumption.
one quick question, like the
Yes.
you mean the 1 megabyte of secrets is like actually a serialized secret. So the secret in memory will be even bigger, right?
Even bigger, yes, yeah. So roughly, let's say roughly 400 megabytes of data, more or less. So before the test, like the steady state, the API server consumed, let's say roughly 4 gigabytes of memory. Then I started the test with 2 informers. That one, it needed 1 gigabyte more, which is not bad because 1 informer had to download at least 400 megabytes of data. Then I tried with 4 informers. It needed more. It needed 3 compared to the steady state. So slightly worse. Informers would need 1.5. Then I started with 8. And the API server consumed 6 gigabyte of memory. And roughly at that point, I started the test with 16 informers, and it failed. I also lost the node that the API server is running on, and I lost both, so the API and the node, because the API server used all available memory on that node. And as we dig more into that issue, we realized that API server actually allocates memory in a few additional places. So it's not only the data it needs to bring from etcd, it's much, much, much more. The first allocation we saw was in etcd client, then during unmarshalling to unknown object, few smaller ones during conversions, and one more at the end when we serialize secrets into protobuf. And that one is a bit special because it will occupy memory as long as or until the response is written. All previous allocations will be eventually garbage collected, right? But the issue was if the spike is big and sudden, GC won't have a chance to do its job. That's why I lost my server, and that's why I lost my node. So our initial response to that was, okay, so let's try to tune PNF. But we realized that there would be at least a few issues with that. So first, we would have to come up with a perfect cost consumption function, right? So you saw the margin is very tight. Only a few requests can break the server. But assuming we could do that, then that would mean we would have to slow down the server to handle just a few requests at a time, probably 10, right? Next thing we tried was, all right, so maybe we could prepare a function, maybe a filter or something that would measure available memory. And if available memory would be low, it would simply protect and repel the request. And protect the server from failing. That didn't work out, mainly because the language itself, Golang, doesn't provide any methods of enforcing memory limits. So our next idea was, all right, so maybe we should use streaming. So stream individual objects, not a huge list. But that initially wasn't that clear. So we thought, oh, that would require changing etcd. Might be difficult. Then API server itself, maybe clients. So huge investment, right? No one would do that. But as we thought more about the issue, we realized that we could use already existing watch requests for streaming. And then we reached out to Wojtek. He gave us essentially a few pointers. And let me show you. Oops. No. That way. Oh no, this one. And this is what we did. So we added a new mode to informers. You can also think about it as we replaced the initial list call with watch call. Normal watch call. What's so special about it is just an additional flag as a query param. And the watch request goes to the watch cache. We then go to etcd and read RV. Then we read initial data from memory, and we start streaming to informer. And then at the end, we send a bookmark with the RV we got in step 2. And then once informer sees the bookmark, it simply ends the connection. It updates its internal store. It takes the RV from the bookmark and starts a new watch request for new events. So let me show you this picture. Maybe it will show it slightly better. So this is the watch cache.
Sorry. Okay.
Yes?
One quick question. Do we really need to stop the watch request after receiving that bookmark, or can we just like continue using this?
So that's a really good question. I did that because if you need to bring a lot of data, it will take time. So I didn't set a timeout. So it can take, I don't know, even 1 hour to bring the data, okay? Mm-hmm. But for the second call, I decided to actually start a new quest and set a timeout. We can decide which is better. I don't know. I did that way. mainly because it can take a long time to bring
I see.
the data.
Yeah, I think it's a detail we can discuss maybe offline also. Yes, but okay. Thanks for the explanation. That at least I understand why you did.
Yeah. All right, so this is the watch cache inside Kube API. And as you can see, it has its own reflector, that guy at the bottom. It brings data from etcd and stores in memory that place. So when we received a watch request from the reflector, we would contact etcd and get the latest RV. Then we would read initial data from memory and we start streaming to Informer. And then we start sending any events we might have received while we were streaming init events. And we stay in that state. And we stay in that state until we get an event from etcd that will have RV resource version that is equal or greater the one we got in this initial step. And this is important. This is for ensuring consistency. There is existing bug, Wojtek knows about it, time travel essentially. So this is what we do to make sure the cache is consistent. And once we have that RV, we will send it as a bookmark to Informer, and that ends the first connection. So here are the results we got. So this is again a graph that shows memory consumption of an API server during the same test. Used the same metric. It was the same setup also, so the same amount of memory, the same CPU. And with 8 informers, the server needed a few hundred megabytes of memory. In the previous case, it needed 6 gigabytes of memory. Then we repeated the test with 500 informers. As you can see, the API was stable, all informers have synced. And then we repeated the test with 1,000 informers. The server allocated in that case a gigabyte of memory. Again, it was stable, all synced. And this is pretty awesome, right? So informers had to bring 400 gigabytes of data over the network. So huge amount of data. And also this is already 100 times better than the previous solution, right? Then we repeated the test with 2,000 informers. I'm not sure if you can see because I cannot, but it failed. That test failed. And it failed due to exactly the same reason it failed previously. So the API server used all available memory. Simple as that. But that tells us at least a few things, right? So we only delayed the issue. So before we needed 10 informers, in this case, we needed at least 1,000. It also tells us that probably memory is, finite, and you need to have some protection in place. Otherwise, you will always use all available memory, no matter what. It also tells us that given, the size of individual objects, so 1 megabyte of secret, right? And the number of informers, 2,000. So you should allocate roughly 2 gigabytes, no more. But this is not the case. The spike is much, much bigger. So that tells us there are some additional allocations. And we managed to take a heap profile dump during a test. And we saw additional allocations. So we saw allocations in raw serializer and serializer. Both are protobuf encoders. We created this picture, this diagram to visualize the issue slightly better. So this is the watch cache inside Kube API server. It simply gets data from the storage layer. So in our case, this is the watch cache, and simply streams back to the client as individual events. And we saw that the first allocation happens when we serialize inside serializer, when we serialize objects, in that case secrets, to protobuf. And that allocation is a little bit special because it won't reuse memory. So the more objects you serialize, the more memory you need. And it will put pressure on GC. And that memory can only be reclaimed by GC. The next allocation happens when we need to store the output of serializer. And that one is optimized. So it will reuse memory for the whole watch request. The next allocation happens when we need to serialize watch event to protobuf, and this is inside raw serializer. And this is exactly the same story as with the first one. So memory, it won't reuse any buffer. It will, per object will put pressure on GC. Only GC can reclaim that memory. And the last allocation happens when we need to store the output of raw serializer, and and then we send data to clients. So those allocations in the red circles are very dangerous, and they require GC. And I think that's why we lost the server, because the GC didn't have a chance to kick in. So if we could optimize these guys, probably using the same technique, reused buffer, we would lower the memory down, and we would, scale even further. So, to sum up, right? So this is not only about the test I did. It happens on production clusters. So in fact, this afternoon, we had a customer case that looked exactly as our issue. So a huge cluster, sudden spike in memory, CPU pressure, crash looping pods, unstable cluster. And this is pprof from that cluster. And as you can see, all allocations happen during list calls, right? And sadly, our response to that is always try to lower down the size of your cluster, or try to find out the clients that make those list requests. Probably adding more memory won't help, as few requests can essentially break your server, right? So here's a link to the PR. I managed to get all E2E test green with a few hacks. It's just a prototype. I don't have a cap yet. It was only applied to informers, but we could easily extend it to client Go. So we could change all list requests to use streaming. And without those optimizations, even as it is right now, is already 100 times better than the list-based solution. And also, last but not least, I know on the last SIG API machinery call, Mike proposed to change the system so that informers always use data from the watch cache. So this solution overlaps with streaming, right? And it's really hard to say how it would look like and what exactly would have to be changed, since no one has done it. But it seems it would require actually less work, right? Because informers already know how to do paginated list to API server. So we don't need any changes there. So it wouldn't also require solving the versions queue issue we need to address with streaming. So the new informer needs to know how to talk to the old server. Both solutions would require fixing the watch cache to provide consistent responses. It also seems that it would require breaking up initial data, the data we store in memory in the watch cache, breaking them into pages. But it also seems that this solution would be less effective. Assuming there are no additional allocations, And I don't know if they are not, we will have to check that, right? But assuming they are not, then that means we would have to allocate a memory that would store all objects that fit a single page. And by default, the page size is 500 items, I think. So in our scenario, that would mean at least 400 megabytes of memory for a single call. And yeah, that's all I have for you today. So let me know if you have any questions.
Yeah, so actually I have one question. So I'm wondering, how does it affect latency of, let's call this like new list calls versus old list calls?
Yeah, so Stefan probably can give you more because he thought about it, but we think it would be actually faster.
Yeah, I hope so.
Yeah.
But I'm just wondering if you have some numbers.
Yeah,
we
I
haven't
don't
measured yet.
have.
No. But the point is we don't have to decode from etcd. At the moment we go to etcd, obviously. We have some overhead for events. So there is a frame around objects, obviously, as well. There's a frame for protobuf, I think, for events, like there's a header of the size. So there are some bytes in addition.
But also there is a important optimization inside the watch cache, right? So we cache serializations. So perhaps maybe in the future, if maybe we could do something like that and, you know, serialize an object only once and then stream serialized objects, maybe.
Yeah, so currently
But
it doesn't fire because we are only reusing the serialization when actually sending the current event. Like I'm not sure how to frame it in a more
go to the picture. You see it on the left side.
On the left side. Yeah, exactly.
Yeah.
So
yeah, exactly. So but yeah, I think it shouldn't be that hard, like to actually reuse that mechanism for this purpose too. So yeah, but basically, like I wanted to get back to like your ask about my opinion. It's exactly matching what I would do, and I'm like definitely supportive for that. I didn't look into the PR and probably will not look like this year because I'm going on vacation, like starting Monday. But I definitely, if you have time and if you are interested, I definitely would like you to write the cap and like I definitely would be supportive for that. I may have some opinions about like some lower level details, but at the high level, I'm definitely supportive for that.
All right, so great. So yeah, we can prepare a cap and try to implement that.
Cool. That looks great. I mean, I was expecting significant difference, significant improvement, but to be honest, I wasn't expecting like 100x better. I was more expecting like 10x or maybe 20 or something, but this looks great. And I think it has a potential to if we invest more into that, I think it has a potential to be even better than 100x.
Yeah, so my hope is it would be constant. A few allocations here and there, but it should really scale. If we can, you know, if we can fix this, then I think it would scale even further.
I just pasted a link to the chat to one PR, which is like very hacky now, and it's not mergeable in this state, but it's something that you may want to try. I think it's basically getting rid of the top one from your graph from your slide. It's basically I think it should be fixing the that one, I think, yeah. Or no, this one is deep copy. I think it was
no.
Sorry, I think
you mean the raw serializer one and the other one?
Yeah, this one, yeah.
Because
from this slide, this one, I think, yeah.
Wojtek, we talked to you some weeks ago also about this deep copy. Maybe can you go back, Lukasz, to the the block diagram, the first one? That deep copy, you might remember, it was about self-link, that this goes away, or is basically already not used anymore. So there is a deep copy in the watch server, right?
Yes, yes, yes.
Yeah, and we should get rid of that because, of course, this is also very harmful.
Yeah, I agree. I mean, it was pretty much used only for the self-link.
Yeah.
So yeah, I think we should be able. Well, hopefully, I didn't have time, but hopefully I want to get back to this discussion, and hopefully in 1.24 we may be able to get rid completely of self-link. Then it would just be simple. If not, like, we should probably gate it by the feature gate anyway. So but like, I mean,
yeah, and
if
not, so I had this PR where I refactor a little, so it gets obvious when you need it and when you don't need it.
Yep.
So even with that, we have a way forward.
So the test I did was without deep copy, so I already had that fix in place. So it's important. But yeah, we can push it.
There's a question about skew. So an old server, of course, doesn't know a list option or whatever we use to pass a new flag. So either we build something into old versions, basically today in 1.24, which rejects the future flag. Then Informer can just fall back to another normal list.
Yep.
But we need to think about that.
Yes, I agree.
And of course, I mean, this is a complete replacement for most users of pagination, right? We don't, I mean, there are UIs maybe which still want that because it just fits their patterns in the user interface, but servers will use streaming.
Yeah, I think it's UI, maybe kubectl will still use it because it's potentially more convenient. But yeah, I agree. It should replace most of the usages of paginated API. Yes.
And about watch cache based pagination for list and consistent, that's what Mike suggested. We have an idea to do that. It's easy, but it won't solve this problem, right? I mean, it's just a factor better than before, but it's still huge page size times object size.
I would probably say that if we do this, then I would even don't bother adding pagination to the watch cache, and just like for the requests that will be requesting a paginated list, I would just like send them to etcd directly in those cases. So, because those, like, once we address informers, reflectors, and all of that, it will pretty much boil down to custom code, which still can be a lot of that, but maybe we can then much better protect it with a priority and fairness and so on and so on. So yeah. But yeah, this looks super promising to me.
Yeah, I agree. It looks great.
All right.
And in terms of like design and stuff like that, it really matches like what how I was envisioning that, which is also great.
So thank you, guys.
Cool. Thanks a lot for presenting that. This is super awesome, and like please keep me in a loop for like your further work. I'm happy to help with reviews and potentially convincing API machinery if they will have some concerns or whatever, but hope not. But just in case, yeah, I'm happy to help with probably not implementation itself, but like with reviews and stuff like that. I'm definitely happy to help.
All right. Yeah. So I think the next step is cap. Let's get details right, and then we can start implementing. So I'm happy to push it. So
Awesome. Yeah, that's great.
and-
So one more quick question, like, are you planning to, or is your goal to have it in 124? I mean, both the cap or an implementation, or do you think it's like too much for targeting for 124?
I don't know, hard to say, but I think I could concentrate on that. So maybe there is a chance we can merge it. So if nothing
No,
else
I'm just,
perhaps,
I'm
then
not, I'm not trying to
I mean,
push you. I'm just asking, like, to understand, like, what are your plans here, and like how much?
Under a feature gate, for sure, I would try to get that in. Whether we open it up, we can decide.
Sure. Yeah.
Okay. Yeah.
Yeah, I think given that it will be like an API change, because we will be adding this new option, I think it will go through alpha anyway, like disabled by default alpha anyway. So I think that the risk there is fairly low. So if we could merge the implementation, then that would be great.
Most important is that we get this queue mechanism in place, that we have an option name, and we open that up like reject calls, which use that even now without feature gate.
Yep.
Yeah, so that would require agreement on the flag, the name. Once we have that, we can, we can reject, and that would help solve the issue. At least that seems the first thing I would try. Maybe there's something else we could try, I don't know, but that seems obvious and easy to do.
Cool. Yeah. Thanks for presenting that, and thanks for working on that.
Thank you too.
Yeah, and I guess we can also probably help with some scale testing later, right? Like in terms of our load test and latencies.
Oh yeah, that would be, because that would be great. Test I did is synthetic test that I carefully crafted to exercise the path I know. It would be nice to see it in real scenario. So hopefully, I don't know, maybe
our tests are also synthetic bars, but are kind of like simulating the real clusters. So.
Okay.
But some average value is what we really would like to see, like in a normal cluster which doesn't do malicious things. How will this impact memory consumption?
Yeah.
So do we actually have metrics available in CI? So can I download metrics and compare what it was before and with my PRs in terms of memory consumption?
So for your PR, there is only a press submit running on cluster that has like 100 nodes. And on CI, we have clusters with 5,000 nodes and more objects, more load, basically.
Okay. So I could start with 1,000, okay.
It was 100, actually.
100, okay.
Yeah. Okay, so I don't think we have any more topics for today. So thank you for presentation, and looking forward to see it in 124.
Fingers crossed. All right. So thank you for listening. See you. Bye-bye.
Thank you.
Thanks.